The next pattern of resonance that we're going to look at is what you do when you're dealing with an allylic positive charge. And so that's going to be very similar to what we already saw when we were looking at that allyl or allylic carbocation. When we're drawing resonance structures going from one to another, and we have an allylic positive charge, you only end up needing one arrow, compared with what we just previously saw for dealing with an allylic negative charge, where we needed two arrows to go from one resonance structure to another. So if we look at an example here, we actually have multiple double bonds, and they're said to be conjugated because they're separated by just a single bond in between them. We actually can draw a few resonance structures for this molecule. So starting with our double bond, starting where the electrons are at, we draw our arrow, our curvy arrow, pointing to where they're going to go to, and the electrons are going to head towards that allylic positive charge. So then that would lead us to drawing our first resonance structure. So we draw our resonance arrow. And then now our pi electrons are going to be right here. We haven't touched the pi electrons right there, but our carbocation is now on this carbon in this position where the double bond was. And we can actually have another resonance structure that we can draw since we have this conjugated molecule where we have a bunch of sp2 hybridized carbons. So we can actually move that other double bond now. So we can take the electrons, start here, those pi electrons, push them towards the allylic carbocation, and then that gives us our final resonance structure, which now we have our double bonds here and our carbocation here. But in each one of our individual resonance structures, when going from one to the other, we only needed one curvy arrow in order to move from one to the next. And that's what you'll see whenever you're dealing with this pattern of having an allylic positive charge. The next pattern is when you have a lone pair adjacent or next to a positive charge. You will only need one curvy arrow to go from one resonance structure to the next. And this will explain how the formal charges are affected by electron movement. So if we look at some examples here, we have an oxygen which has a -1 formal charge, and we have a carbocation which has a +1 formal charge. We can take one of those lone pair of electrons on the oxygen and move them in between the carbon and the oxygen to create a carbon-oxygen double bond. So this actually creates a better resonance structure when we start comparing who is the best, because now our oxygen has a 0 formal charge and our carbon has a 0 formal charge, but these are still two resonance structures. So here's another example of having a lone pair next to a positive charge. We can take the lone pair of electrons on the oxygen and move them using a curvy arrow over to create a double bond in between this carbon with a positive charge and our oxygen. We can do that because carbon doesn't have 4 bonds. It has 3 due to it being a carbocation. So we're not breaking the octet rule by doing this. So then we now have an oxygen-carbon double bond. There's still just that one hydrogen coming off right here that's not being shown. We're left with one lone pair of electrons on our oxygen. So our oxygen ends up having a positive formal charge instead of our carbon now. Now our carbon has 0 formal charge. So we're going to learn next how to analyze the two resonance structures, or even if you have more of them, to decide what is the better resonance structure and what's the major contributing resonance structure. So for example, in this one on the right, is it better to have a positive charge on carbon, or is it better to have a positive charge on oxygen? Oxygen is more electronegative. Carbon is less electronegative. So if one of them had to be positive, it would most likely rather be the carbon, since it's less electronegative, leading to the structure on the left being the better resonance structure. We just said that when you have a lone pair adjacent to a positive charge, you usually need to use one curvy arrow to go from one resonance form to another. And usually what will happen is the positive and negative charges will essentially cancel each other out, and you will create a double bond in between those two atoms. But just like all rules, there are sometimes exceptions. So if we look at something called the nitro group, which a nitro group is an NO2 group, and the structure looks like what you see in the upper right-hand corner. We have a nitrogen that's singly bonded to one oxygen, and that oxygen has a -1 formal charge, and it's doubly bonded to another oxygen that has 0 formal charge. The nitrogen has 4 bonds and no lone pairs, so it has a +1 formal charge. If we were to try to start to draw the resonance structures for our nitro group, imagine if we were to just take one of the lone pairs and push them in between the nitrogen and the oxygen. That would give us a structure that looks like this. We would still have our double bonded oxygen. Now our nitrogen would have a double bond to the other oxygen on the right side where we moved those lone pair of electrons. And it would still be singly bonded to, let's just say, something else that it's attached to. Now, we cannot just use one arrow because look at our nitrogen. Our nitrogen now has 5 bonds to it. And 5 bonds means it has 10 electrons around it. So this violates the octet rule right here. So we have to use another arrow in order to actually draw the resonance structure for something like the nitro group. So this is where combining everything you've learned so far kind of comes into play. If we redraw what we started with here, how we could go from this first structure to our resonance structure would be to take one of our lone pairs of electrons, push it in between the nitrogen and the oxygen, and then immediately take another set of pi electrons that is in between the other nitrogen and the oxygen right here, and push those over to the other oxygen. And so then if we draw our resonance arrow, the structure would look like this. It would basically look like the mirror image. We'll now have the left oxygen with 3 lone pairs of electrons on it, so it'll have a -1 formal charge. And the right oxygen now has no formal charge. Our nitrogen has 4 bonds and no lone pairs, so it still has a +1 formal charge. So this is an example where we had to use 2 curvy arrows in order to draw the resonance structure. The nitro group is just an exception, and sometimes you'll come across exceptions to these rules, but it's still important to be able to learn the general patterns in resonance. The fourth pattern of resonance is when you have a pi bond between atoms of different electronegativity. And this is actually the exact opposite move of what we just learned, where we had a lone pair next to a positive charge. So the pi electrons in this double bond will be more attracted to the electronegative atom rather than the more electropositive atom. So when we have to decide who the electrons go to, we want to just compare the electronegativity of the 2 atoms. So if we look at an example here, we have a carbon, which is more electropositive, doubly bonded to an oxygen. So we could take a set of those pi electrons and move them up to the oxygen because the oxygen is the more electronegative atom. And so this would create a separation of charges. Like I said, this is the exact opposite move of what we just saw. So that would now put 3 lone pairs on the oxygen. Oxygen would have a -1 formal charge. And our carbon would now be electron deficient. It would not have an octet, so we have a carbocation there. And still notice if you add up the formal charges of carbon and oxygen, we have +1 and we have -1, so they add up to 0, which that corresponds to this structure, which has 0 formal charge. So the combination of those formal charges is neutral because we have a neutral molecule. Another example, we have a nitrogen with a lone pair of electrons, 3 bonds, so nitrogen has 0 formal charge. We have carbon, which has 4 bonds, 2 single and 1 double, so 0 formal charge here. We could split them and separate their charges by moving the pi electrons between carbon and nitrogen. And so nitrogen is more electronegative than carbon. So when we move the electrons, we're going to move them towards the nitrogen. So we'll take our pi electrons, push them up towards the nitrogen, and that would leave us with a single bond in between that carbon and that nitrogen. Our nitrogen will now have 2 lone pairs of electrons on it. And so our carbon will be a carbocation with a positive charge. This bonding pattern for nitrogen was 2 bonding pairs, 2 lone pairs, and it had a negative formal charge. And so when we compare our resonance structures, the one on the left is actually better because it minimizes the amount of formal charge, but the one on the right is still technically a valid resonance structure. Sometimes you'll be starting with the one on the right and moving the electrons to give us the one on the left, as we did in the previous pattern. The last pattern of resonance is when you have conjugated pi bonds in a ring. And so the only example that we're going to look at right now is that of benzene. But if you have this, every atom in the ring must have an unhybridized p orbital that can overlap with its neighbors. So you're going to have a bunch of single and double alternating bonds. And so when we show the movement in something like this, we actually have multiple arrows that we have to draw, multiple curvy arrows. So we can take these pi electrons right here, and we can push them in between this carbon and this carbon. But then this carbon right here would have too many bonds. It would exceed an octet. So then we would have to take the next set of pi electrons right here, and we would have to push those electrons right over here between this carbon and this carbon. But then that carbon would have more than an octet. So then the pattern continues. Lastly, this set of pi electrons would have to get pushed in between this carbon and this carbon. And so what that leads to is a resonance structure that just alternated where all the single and double bonds are located. Notice in the first one, you have them here, here, and here. And then in the resonance structure, your double bonds are now here, here, and here. So they all moved locations together because they were conjugated. So let's go over a summary of the 5 major patterns in resonance that you're going to want to be familiar with. The first one we saw was an allylic lone pair. So the lone pair of electrons is in the allylic position when compared with the double bond. So we needed 2 curved arrows to go from one resonance structure to another when we were dealing with that pattern. One to move the lone pair of electrons down, and then we had to actually move the pi electrons of the double bond over so we didn't exceed the octet rule. The next pattern is when you have an allylic positive charge. So you have a positive charge next to or one over from the double bond. So we pushed our pi electrons of the double bond over towards the allylic positive charge, so that way we wouldn't be exceeding the octet. And we only needed 1 curved arrow for that move. Next, we had a lone pair next to an adjacent positive charge. We were able to take a lone pair of electrons and push them towards that positive charge, creating a double bond. And we usually only need 1 arrow for that move. The exception we saw was the Nitro Group, where we ended up needing 2 arrows for that. The next pattern is when you have a pi bond between 2 atoms of different electronegativity. The pi electrons got pushed towards the more electronegative atom, and that only took 1 curved arrow. And then lastly, you could have conjugated pi bonds in a ring, and this example was that of benzene ring. Here we needed 3 curved arrows to move all of the pi electrons either in a clockwise or counterclockwise direction. When you start studying resonance, it's a little tricky because you need to combine everything that you've learned so far. You need to understand line bond structures. You need to understand how many hydrogens are not being shown off of a specific carbon atom. You need to understand formal charge. You need to think about how pi electrons can move when you have atoms that are overlapping with sp2 hybrid orbitals and how they can delocalize throughout them. So really take your time to understand this because it's important in reactions going forward in this entire class. So take your time and really combine all of those concepts together and practice with resonance. Let's try an example before we wrap up talking about resonance. So we are given a molecule here, and we want to try to draw the various resonance structures. And so always think about maybe what are those patterns that we discussed, and how can we move our electrons around without violating any of the rules using these patterns. So starting off, let's look at the oxygen on the lower right-hand corner. That oxygen has 3 lone pairs on it, so it has a negative formal charge. And right now in this structure, we're seeing formal charges and we're seeing lone pairs to kind of help you out right now. So one of those lone pairs, we could say, is adjacent or it is allylic to this double bond right here. So this is one of our patterns. We can take the lone pair of electrons and push them to create a double bond in between this carbon right here and our oxygen. But then that carbon would have too many electrons around it, too many bonds. It would exceed an octet if we don't move the pi electrons of the double bond now. So then next we would take them and move them to this position right here, that carbon. So we're going to draw our resonance arrow, and we're going to redraw our structure. So we haven't touched anything else yet. We still have our nitrogens all the same. Now we have a double bond in between our oxygen and that carbon. Our oxygen has 2 lone pairs on it, so formal charge will be 0 here. Our electrons, our pi electrons right here from our double bond ended up right here on this carbon. And so that carbon now has 5 electrons around it, so it has a -1 formal charge. And we still have a positive charge here. So now we're at our second resonance structure. And the next thing I see is that I have a positive carbocation right next to a negative carb anion. So I have a separation of charge there. I can take that lone pair of electrons on that carb anion and I can push them in between the carbocation and the carb anion. So my next move would be to draw a curvy arrow starting where my electrons are at, heading where they're going towards, and push them in between the carbocation and the carb anion. I can do that because I'm not going to be exceeding an octet anywhere, because coming off of my carbon here, there's only 1 hydrogen. So it can accommodate a double bond in between those 2 carbons. So next we would draw our resonance arrow, and we would redraw our molecule. And we now have a double bond right here. There's still 1 hydrogen coming off right here, and our oxygen still has a 0 formal charge. We haven't changed that yet. Now, when considering our carb anion and our carbocation, we had a plus charge and a minus charge right next to each other. We moved a pair of electrons in between them. Notice that now both of those carbons have a formal charge of 0. 0 here and 0 here. That's because we took those 2 charges and put them together. We can continue on around our ring. We have a nitrogen that is allylic to our, well, a lone pair of electrons on the nitrogen, I should say, that is allylic to our double bond. And so we can move those lone pair of electrons in between the nitrogen and the carbon. But then if I stopped there, I would have too many bonds to carbon right here. I'd have 5. So I have to take the pi electrons of the double bond and they'd have to sit as a negative charge back on that carbon where they essentially came from. But this is just another resonance structure. We could have actually started up here at the top when we were starting to draw them. There's no specific spot where you have to begin showing your resonance. So we have our nitrogen that's double bonded here now, this carbon. So our electrons ended up right here back on that carbon they came from. That carbon now has a negative charge. It's still not exceeding an octet though, right? It has 3 single bonds and a lone pair of electrons around it. So it still has 8 electrons surrounding it. And when we look at our nitrogen though, on the top, now that has no lone pairs of electrons and it has 4 bonds. So it's going to have a +1 formal charge. So in a way, we separated the charges again. Now this appears to be our last resonance structure that we can draw. If we move our lone pair of electrons, we would just be heading back towards our oxygen right here, going back to what we started with, basically. So if we take that lone pair of electrons and push it in between carbon and carbon there, we'll have a double bond again, and our oxygen will have a single bond and a negative formal charge on it again. So I suppose this would be our final resonance structure that we can draw. All right, now one other question is why did we not touch the lone pair of electrons on the other nitrogen or the double bond next to that? So this region of the molecule. I can't really push these electrons right over here because there's two hydrogens coming off of that carbon, and that would then exceed an octet, so those can't go there. Plus that carbon right there is not sp2 hybridized, it's sp3 hybridized. So there's no unhybridized p orbital associated with it, so you can't have delocalization of those electrons there. And then same thing going the opposite way, kind of. I can't push those electrons on that nitrogen there because I already have a double bond there, and that double bond can't move anywhere else because this carbon right here is sp3 hybridized, so no unhybridized p orbital. So I can't do anything with that region of the molecule. That's not going to participate in resonance. The major part we saw that was participating in resonance was through this spot, the nitrogen on the top through the oxygen on the lower right hand side, because there was a bunch of regions where the electrons could delocalize because of having an unhybridized p orbital available.